So people on Zoom hear us okay? Thumb up if you can hear us.
Probably they cannot.
Yes, we can hear you.
Okay, great. Okay, so let's get started. So it's our honor to have Professor Song Gao to be the speaker today at the past seminar. Professor Song Gao is professor in the Department of Civil and Environmental Engineering at the University of Massachusetts Amherst. She received her PhD and master in transportation from MIT and bachelor degree in civil engineering from Tsinghua University. Professor Gao's research advances experimental studies and econometrics models for behavior for choice behavior and behavior models in transportation networks, as well as optimization algorithms in stochastic network systems. So she has played active leadership roles in various professional society committees that include being a chair in the Transportation Research Board and chair in the Informs TSL interest group. Additionally, she was also selected as a UMass Advanced Faculty Fellow. Professor Gao serves on editorial board of leading journals that include Transportation Research Part B, Journal of Intelligent Transportation Systems, and also Transportation Science. So let's welcome Professor Song Gao and for address.
Thank you, Manshi, for the introduction. Thank you for coming to my talk today. So as you have seen from the title, so I'm going to talk about trying to figure out how drivers, whether the taxi drivers or Uber Lyft drivers, go about looking for the next passenger when they drop off from the previous one. And we do this in a network-based model. So that's sort of in contrast to what the literature has been done, or like a hexagon-based. So we also do the joint estimation of both the behavior parameters as well as the system level, sort of the how the matching between passenger and driver happens. So this parameter in that system model will do the joint estimation, and also under a Markov decision process framework. So the okay, now the usual line, so I'm not going to read through that. The motivation is, of course, we, from the system perspective, effective driver relocation reduces waiting time, improve profit, also improves sort of the overall system efficiency. And in reality, of course, drivers are very different. They adapt all kinds of strategies. So the idea is trying to come up with a empirically estimated model of their behavior, which can be a building block of any prediction models that we would like to use to evaluate either operational strategies that adopted by the platforms or policy changes adopted by government agencies, especially considering that, as trading could be sort of becoming ever more prevalent. So just a quick sort of overview of what we're doing here. The inputs are, we're given the spatial distribution of passenger demand, spatial distribution of vacant vehicles, basically sort of what my competitor's distribution is. So this is from the viewpoint of a single driver, right? So we're trying to understand an average driver's behavior. So there is this demand distribution, supply. Basically, there are other vacant taxi vehicle distribution. There's also the observed trajectories of vacant and ride sourcing vehicles. We have two models. This one, the driver routing decision. So at each node, which next link I should take. So this is as infinite horizon Semi-Markov decision process, in the sense that the decision is based on my immediate next sort of reward, as well as the, if you wish, in this case, it's like reward to go, right? So all downstream rewards rolled into sort of one value function. There's also the passenger driver matching model based on sort of the demand supply ratio, because that determines sort of my transition probability into whether matched or not matched. Output is the driver utility parameters and the matching model parameters. So it's an empirical study. Now, for the driver's decision process, we use a Markov decision process, but with a little bit twist. So we have a network that with nodes N and links A, and the semi-Markov decision process, similar to MDP, has the space, action space, transition probability. But in addition, there's the holding time in the sense that there is certain amount of time that we left before the transition happens. Okay. Other than that, everything else is the same as MDP in the sense that my transition probability only depends on my current state. And we only model the vacant taxi. So a higher taxi is assumed to just take short pass to the passenger destination. And basically we have like a super link also. So the state space, we have two parts. I'll talk about the observable state first. So the node the taxi is located at, that's the observable state. So it's just reached the location. We start from simple formulation. So we don't have other sort of contextual information at this point yet, so just the location. But since we do sort of assume that the driver also knows some kind of distribution of the supply demand, so that can implicitly there is some kind of demand supply contextual information also included as part of the location information. Right? The action is to take one of the multiple outgoing links, right? So in traffic network, that's only 3 or 4, right? 5. Once you take that link, there is 2 possible transition, 2 possible categories transition. Either you're not matched, so you just end up in the next node of that link you choose, or you are matched with a passenger, and then you transition to the destination of the passenger. Right? So the transition probability from current node I to the next node L, the L can be either the next node of the link or the passenger's destination. Of course, depends on the passenger driver matching probability. Right? So it's also parameterized, which we'll explain very shortly. If you are if your next node is just if your next state is just your next node on the link, then you're not matched. So M here is a matching probability. So it's one minus that. But if you are actually matched, meaning that you're going sort of away from your next node, then the transition probability is the matching probability times the destination probability. So the passenger destination. At this point, we're not modeling the destination probability. So it's basically just the observed frequency. Okay. So we focus on the matching here. The matching probability is related to 2 observed quantities. So the pickups, which is the lambda represented here. So that's the average passenger pickup rate. That's both per time unit and per area unit. And then it's multiplied with the travel time of that link. So that gives you the number of passenger arrivals per time unit, per area unit. And then it's divided by the competing to balance the other vacant taxi density. And that ratio then plays a role in terms of, how likely and random vehicle on the link during the traverse time will be matched with a passenger. So we use the negative exponential function. It's a reduced form functional form. It's not like we derived from any sort of Turing theory or other mechanistic model. It's just a reduced form that makes sense and can fit the data properly. So the theta 2 here is the parameter that we need to calibrate from the data. So that controls basically, in a sense, like some kind of spatial friction. The idea is that, when you're looking for the matching, it's not like when you have the same number of vehicles and passenger in the same row, then you get matched with 100%. So there's sort of this friction in the searching for the other part.
Tau is
Tau is the travel time only.
Tau.
Yeah.
So, because it's a semi-Markov chain, right? So you model the time as continuous.
Right.
And is your matching action only triggered when there are new passengers in the system? Like, when is the decision making?
Oh, the decision is at each node.
Is at each node?
Yeah,
But-
at each node when the vehicle is vacant.
Okay, so it's triggered by vehicle arrival of a node and being vacant.
Right, yeah.
So there is no fixed discrete time step where decisions are made.
Right.
Right, thank you. So then what is the holding time?
So this, hey, here is just the travel time of the link.
Okay,
Well, if you're not matched, that's travel time of the link. If
Okay.
you are matched, then it's basically the time of the whole hide trip. Like if my destination is to San Francisco, then the holding time will be about 30 minutes.
okay,
Yeah, but if I'm not matched, then it's just the travel time of the current link, which can be maybe only 30 seconds. There's a big disparity in that transition time, so
so you make a decision when the state changes. No matter if it is because of an arrival of a destination or
Mhm.
arrival at the next node, right? So you make a decision whenever you become available the next time.
right.
Okay, great.
Okay, so that's the matching model, and then we assume that the driver has a basically facing this infinite horizon decision process. And there's here the full state, so there's this observable location I, but also the unobservable epsilon. So that's typical that we're assuming discrete models. The arrow terms that affect driver decision, but not sort of observed by modelers. And so driver chooses a policy. So F that match the state to an action. The state includes both observable and unobservable to maximize the discounted return over the infinite horizon. So the idea is that the driver will get a passenger, jump off, another one. So there's like many rounds of pick up and drop offs. Yeah, so the Bellman equation in the full state space is right here. So it's a familiar format that we have seen a lot, except that here we have a random term, the arrow here. R here is the reward or utility function that's parameterized with theta was as a vector because it can include many different explanatory variables or so-called features. And you also then have this with the reward to go, return to go, basically what you do next. And the fact that here we sort of separate the transition probability into two parts where you have just the transition of the observable part, like just from one node to the next, and versus just the transition of the error terms is that there's some underlying assumption right there saying like this two can be separated, and that's the only we need to make the assumption to make this work. So the transition function P here is parameterized with that too, as we talked about earlier. So it depends on the matching probability. Yeah. No, but working with the full state space is difficult, and we then basically take expectation on both sides of the Bellman equation to get. So instead of the big V, we sort of integrate out the epsilon, so we get a small v. And then we also need to do the expectation on the right hand side, and that gives us the social surplus function. Basically, it's a function of a set of values, and the definition here is you add some random term, but you take maximization over the options, but then you then take expectation over the random terms, right? So if the epsilons are IID gumball, then we get log sum, so that we're all familiar with from our discrete choice model versus. So yeah, so once we have that notation defined, then the expected Bayesian equation becomes what we have here. So the big V in the full space becomes a small v in just the observable space, the epsilon is out through integration. And the right-hand side, yeah, this one is also out, but we end up with the surplus function, social surplus function, big G. So, so this is a contraction, so we can then view this is basically viewed as fixed point problem, right? So, right-hand side we have the small v, and through this operation you get the small v on the left-hand side, and that's fixed point problem, and it's a contraction. And the main reason is that because the discount factor here is strictly less than 1, so we need that for the proof of contraction. So then we can just solve for a unique fixed point for any given theta. So this is needed in the estimation. So trying to figure out the theta will be to match the observed trajectory the best. So the estimation, well, specification first. So epsilon, if we assume them to be IID gumball, then the social surface function is the log sum. So we're taking expectation over, sorry, yeah. So log of exponential of the utility function, which includes both the immediate reward and also discounted future reward. Then the choice probability is a logic model. Again, we're familiar with this. I just want to say that the utility function includes the two parts, both the immediate one and discounted future utilities.
Sorry, I didn't follow the notation. So what is A conditional on I?
So the probability of choosing action A, in this case, actually just blink A when you add node I. Yeah, so it's the so each link will have some immediate reward, let's say like revenue or cost, yeah. And then expect, sorry, discount the future reward.
Sorry, what
Yeah.
is theta 2?
Theta 2 is the
Matching.
the parameter in the matching probability.
Oh.
So yeah, that's right. Yeah.
Oh,
Yeah. So the demand over supply ratio multiplied with that theta 2. Okay.
So here you don't consider the pricing part of the.
No, not at all. So in the empirical study, we basically sort of check, during that time of the data was collected, what is the fair structure? So there's, yeah.
sure.
So in the model estimation, so we have assumed, the data we have is the observed state transition tuples, right? So the current state, the action taken, and the next state. And when the current and next state are basically physically connected to two nodes, then there's just no match, right? I'm just traverse this link without being matched, so I'm continuing on. When they're not physically connected, then it's quite far away, means that, very good. Match with passenger and carry to destination. So we write out the likelihood of observing those transition tuples. And there are two parts of the likelihood function. The first part is related to the choice. Right? So given that observed node I, what's the probability of choosing the observed action A? Then there's also by the way, here the theta has no index, means that's function of both theta 1 and theta 2. So both behavior parameter and also the matching parameter. So yeah. And then the second part is related to just the transition, state transition likelihood. So match, so not matched, matched. Sorry, I don't have a slide. Okay, so but yeah, so the algorithm that we use is the BFGS in Python. So unconstrained management problem. But we do need to do some to calculate the gradients. So that another sort of set of fixed quantity equation to do that. And that can speed up a little bit because otherwise BFGS will use the finite difference. Okay. So case study, we have data from Shanghai, China. Read that number, but it's a very big city, the most popular city in China. So row network was over 13,000 nodes and close to 30,000 direct links. So the GPS records is a pretty high frequency with 10-second intervals. So that means we can pretty confidently figure out the trajectory, link by link trajectory of the vehicles. So we do just 6 hours in the morning from a representative working day. There's also a big, very time consuming process of map matching. And so, yeah, this is the things that spend a lot of time doing, but cannot say too much in the paper. So my student, of course, did hard work.
How did you get that, Song? How did you get the data set? What's fantastic?
Yeah, so I have a collaborator who used to work in a company in Shanghai, and he got access. Yeah. So we extracted about 6 million transition tuples from the data. So that's a map of Shanghai, and it's well, not map, but pick up heat map. And so the red part or the dark part of the city center, and you have some major transmission hubs, the railroad station, and this one airport in the city. And then right here is the Pudong International Airport, a bit out of the city center. So just a little bit statistics. We have here the occupancy rate. So this is the percentage of time that a driver's actually carry a passenger or revenue earning factor. So we can see, like, of course, drivers are very different. We have people who are really either very lucky or just have really skilled, and people are not doing so well. So the average occupancy rate is about like close to 50%, but with pretty wide range. Related to that is the unit profit. So this is Chinese yuan per hour. And by the way, so we basically check the prevailing fare structure in that time, and then we calculate the operating cost. So this is only we only account for operating costs, but not sort of the vehicle ownership costs. So of course, yeah. So a similar distribution.
Does this consider the vehicle occupancy rate?
No, we don't think we don't have that. So but even if you have two passengers, isn't that the same fare?
Oh, I mean, previously you had this occupancy, like what's the percentage that is running empty, right?
Right.
So this profit, you already accounted for half of the time that the vehicle is empty.
Right, yeah.
Okay.
Yeah.
So what is in the operational cost? And
Just-
gasoline?
Just the fuel cost.
Fuel. Okay.
Yeah.
And they're all profitable?
Mm.
Except a little, it looks like a few little people.
Yeah, that's a good question. Yeah, this little bit there, yeah. Yeah, good for them.
Yeah, exactly. It's-
Okay, so first, just some results on the computational side. So like I mentioned earlier, we need to do fixed point iteration to solve both for the time function at a small v and its gradient. So to accept that's computational intensive. To extend that, we do parallel computing, but it's pretty transparent. Basically, like, we do a magnitude operation Python will just use power computing to do that. So that's saved quite some time, but I also try using GPU. The savings not as much as we had hoped, but there's some saving. I think comparing a 16 core CPU and that's a GPU.
Okay, so the main time consuming part is a fixed point iteration. Okay.
Yeah, so we will both the value function and its gradient. The gradient is also it's an implicit gradient because there's no closed form expression. Okay,
So the gradient, you mean a gradient with respect to
theta.
the solution of the fixed point?
The gradient with respect to the parameters that we are trying to estimate.
Oh, yeah, when you say there's no closed form, you need to like finite inference for the problem.
No, so we just because we have it's like just taking implicit gradient, right? So
Oh, I see. So
Yeah.
you do implicit functions.
yeah, just do the derivative on both sides of this, and then you just have to solve that fixed point. It's another new fixed point problem. Yeah. Okay, so what do we include in the utility function or reward function? So we have the first four are the behavioral parameters. The last one is just the matching function parameter. So we have the fare. So that's the expected fare. But because the expectation is on the transition probability, so we have some already estimated matching probability parameter. So we basically just separately estimate theta2 from just maximizing the second part of that likelihood function to get theta2. And then we calculate the expected fare based on that. We have expected operating cost and that just the fuel cost. And we also have a variable called link size. So this is a version of the path size in path choice model. So the idea is when you use logit model, you assume ID Gaussian distribution of epsilons, but routes usually are overlapping, and so that assumption generally doesn't hold in root choice. So the various way to correct for that, and the easier option is to I still use logit, but I will add a term called that corrects for that overlapping. So if two routes are overlapping, I'm going to try to reduce its probability to account for that they're actually sharing some error terms, the correlation. So the link size here is a version of that that reflects the level of overlapping between various alternative policies. And we also have a link count. That's actually just says for any option outgoing arc, that's just the number one. But because the utility function includes both the immediate reward and discounted future one, so it actually accounts for the number of intersections on the whole route. And we also have a binary variable to indicate whether it's urban or suburban. And that's in the final model multiplied was the link count. So basically the effect of number of intersections on your route in urban area. So the main model, do I have? Yeah. So let's take a look at the main model first. This is our proposed model, and the first three are some baselines we'll talk about later. So all the parameters are statistically significant. It's great, except that of the link size, which accounts for the overlapping. So signs are expected, positive effect of fare, negative for operating cost, negative effect of number of intersections in the urban area. But what's interesting is that if you look at the values of the fare and cost, the thing is like when we started, it was okay, I'll just do one, it's profit, right? So fare minus cost, and that adds one variable. But that actually imposes this assumption that people perceive the revenue and costs are the same. So it's okay, why not just separate them? And it turns out the absolute values are actually different, significantly different. And the perception for fares seem to be, basically people are probably more attuned to fare or more sensitive to fare than cost. So the reason might be that, the fare is really, you get that number every time you perform a trip. But cost is more hidden, right? It's not out there. So that's just one explanation I have for the two difference, but it's kind of like, if something's displayed, get your attention, you really, get sensitive to that. It's like, the gas price that displayed on the roadside, and even if it's only a very small difference, you get really sort of attention to get attuned to that difference. Yeah, so the next point is about this link size that reflects the overlapping, and it's not significant. So theoretically, we would expect this to be a positive number, sorry, negative number. So the more overlapping that two routes have, the more penalty we should apply to their utility. But on the other hand, people might actually like overlapping. So it gives you flexibility, right? So since in this case that the two opposite rows kind of cancel out in a sense. So yeah. And then we also compare the main model with three baselines. The first one was single cycle. So this motivated by a study in the literature published in Transition Part C. So they also have an MDP model, and they do discretize the time. But the most significant difference is that they stop their decision process when a driver is matched with a passenger. Sorry, the stop process when the driver is matched with a passenger, but they do account for the fare that they get from the passenger. So in a sense, it means that they stop the process when they drop off their first passenger or the next passenger. So we call it single cycle. So our model is really like, after you drop off that passenger, you will continue your next searching adventure. So the idea is to see whether which type of sort of vision process would be explaining the data better. So it turns out that well, here we use a just row square to measure the model fit, and turns out that since drivers can look forward for more than one single cycle. So the idea is that you not only worry about where you get your next passenger, but you also worry about whether you're gonna get another passenger after this next passenger. So that's the first baseline, and the next is the so-called high discount rate. High discount rate means that you discount future a lot. So it's another version of saying drivers are myopic, but it's more kind of like a continuous way of discounting the future, where the single cycle is like kind of very like discrete way. So I just consider my next cycle, and then from next cycle on, it's all zero. This is like, I do still consider many cycles, but I discount a lot. And turns out that's not a very good, at least not as good as the main model, where we have relatively sort of small discount, which means mass future is not discounted as much. Then the third baseline is not necessarily in terms of different modeling assumption, but just estimation. So this sequential estimation, where we do the estimation of the parameter for the matching, the theta 2 first, and then fix that and estimate all these other parameters. So that's not surprising that there's a lot of it's well known that if you do want optimization, it's probably you'll get more efficient use of data than just doing the estimation separately. We also just plot the estimated movement probabilities by orientation. Because the actions are along the arc, so we have to do some aggregation to plot their movement direction in 8 different orientations. So the dark, whether it's dark blue or dark red, are just meaning that more deterministic movement. The light yellow or green or red just means that more sort of random movement. So if you recall from the earlier map, these are the city center, and they generally have more random movement compared to places like sort of more suburban or even rural area. So probably that's because in the high demand city center, where to go next probably doesn't really make much difference. So it's more like a random walk. But when you are in a place that really not very high demand, then you probably very intentional of going to a high demand area. So
Did you find there is a like moderate to long distance reposition behavior?
so it again.
So did you find from the data that people do moderate to long distance reposition decision?
Oh, you mean like how?
would
They are, no, I did not display that statistics, so there's also the searching time, right? So you're looking at like distribution, yeah. So mostly it's around like, I think 10 to maybe 20 or 30 minutes, but there are some very long.
Oh, I see.
Yeah, but it's not necessarily like they are intentionally making long distance reposition. Maybe it's the
I see.
unlucky that day that they don't get matched with passenger for a long time. Yeah, they're like an hour or even like 2 hours, that kind of big
And they
gap.
keep driving this whole time, or do they stop, or,
They keep driving.
because they have to, it must be, because it's expensive to keep driving.
Yeah, but if you don't move, yeah, I don't know. They keep driving, yeah, so. So another popular approach is in literature to study this kind of problem is to do a zone-based MDP model. So basically you divide your study area into some hexagons. Those are the same area, uniform area, and the travel time between the hexagons is also the same. So then you just have an MDP, right? So each transition takes the same 1 unit of time. So my intuition is that, if you do that kind of arbitrary division of the study area, so you kind of ignore the underlying network, and that might, have some disadvantage. So I also compared the link-based SMDP with the zone-based MDP. So of course, there's some inconsistency in the data, right? So the zone-based, you cannot compare the model fit directly because they're based on different data. Resolution of data or format of data. So there's extra data processing needed to basically convert structural data into zonal movement because actual trajectory link by link. So we define some kind of like 4 minutes interval. So within 4 minutes, if you're staying in the same hexagon, your action is labeled as stay, even though we don't know exactly whether the driver is indeed decide to stay or not. Now, that 4 minutes interval is kind of judgment from the modeller's part. Anyway, so we use that data, that 4 minute interval from the literature. That's generally how comparable. And then we compare these two models based on the prediction only, made on the test set. Again, still, we have to process the output for them to be comparable because link model gives link level prediction, zone model gives zone level comparison prediction. Yeah, so there's aggregation on one side and disaggregation on the other side. So we have the comparison on this table here. If we do the comparison based on link observations, not surprisingly, the link-based model would make better prediction. And the zone-based model actually make a much worse prediction, looking at the much smaller adjustable square. Now, if we do the comparison on a zone movement observation. So the zone-based model, that's better. Well, not surprised because it's making the prediction based on at the same level that the model is estimated on. But the link-based model is not much worse. At least sort of the difference is not as dramatic as the other one. So it seems that when you have a more detailed model that accounts for the underlying network structure, is more robust when it's asked to make a prediction at different spatial level that is estimated on. Okay. So let me see, I'm actually going to skip the related work and yeah. So just to conclude that the SMDP framework is adequate in accounting for the variable in time in a sequential decision making process in this particular case. And large network case study shows that computational feasibility of this model, even though we need to solve a lot of the fixed-point problem. So it's a fair operating cost, the number of intersections in the urban area are simulated predictors. Not surprising, but interesting is that drivers perceive the fare and cost in different manner. And there's comparison with base model. Some baseline model shows that there's advantage of considering multiple decision cycles. So it seems that drivers are sort of forward-looking or foresighted to some extent. And there's an advantage of joint estimating both the system model parameter and also the behavior parameters. Yeah, and lastly, the link-based model seems to be more robust than the zone-based model when they're asked to predict at a different spatial level than they are estimated on. Right? So I guess. And this is just some methodological trace that leading to this particular work. So the dynamic experiential models first early work on the by Rust, and then this adaptation to much choice, to transportation in the static and deterministic network by Fostera. And later on, there's Tian's work on like rule choice, also stable choice, but in a stochastic network. Right? So in the static network, it's deterministic actually. The position is degenerate, there's no stochasticity. So later on to extend that, and the current paper is another application to a ride-hailing context. Yeah, so some extensions. So the data set that, as John has asked, great data set, but it's not usually available to researchers. So what if I don't have this high frequency trajectory data? So what do I do right now is to assume that we only have the pickups and drop-offs. So the searching process, you don't observe the full searching process, but you only observe where you actually pick up your next passenger. So that kind of information is available from existing data set like New York City one or Chicago data set. Well, so basically you have a lot of missing information. The idea is to, at this point, to still write out the likelihood of getting matched at a particular location if you start from a unknown previous location. So we'll see whether that kind of process can still uncover the underlying process. Maybe not. Maybe there's too much thing that's missing. We'll see. And also, just from the behavioral side is one single set of parameters enough for a heterogeneous population of drivers, as you can see earlier. The range of the occupancy rate and profit is pretty wide, so probably not, but they're not using the same strategy. So we right now only one average driver, but some kind of latent driver classes could be very helpful, yeah. So, how can a be useful or as part of a mobility system simulation or equilibrium model that can be used for prediction. High performance driver strategy can be used as optimization problem solution. It's basically saying, okay, I don't do my optimization by solving some mathematical programming problem or some other ways. I just look at the highest performance driver and just mimic their behavior. That's another way to do that, or as a basis for driver station support system. So this is really I've been passionate about doing this problem from the driver's perspective. And so I think a lot of research is from platforms perspective, but I think drivers, of course, are disadvantaged in terms of access to data and those technical priority to make use of data. Yeah, so I have a swing grad team with trying to support drivers. I think understanding how they make choices will be a good first step. Yeah, so yep, that's all I have. Thank you. And
Question from the audience, those online and offline.
Go ahead, I actually asked.
Quick question, so like, I'm curious about the results compared with the like 4 or 3 like baselines. I saw like that the performance is majorly about like the final LL like loss. Like, so the main model is like -294, and the others are like -297, -304, if I remember it correctly. Like, so like, I don't know, like, I haven't done research in this area, so I don't know how significant they are. Like, what is the like more of the like more some other metrics that apply in the reality, like how does reflect in the reality?
Yeah, so we also did the cross validation. So basically saying like, yeah, divide data into maybe like tenfolds and the prediction test. But it's the same thing. You're saying like how much of the difference is big enough to say that you definitely have good. I mean this I think usually like at least in discrete choice model literature, a difference of like 0.01 would be a good large enough difference to say that you have a better model. Yeah. But sometimes when you look at, for example, when I look at this on the estimates, they're really not that different, if you wish. But for the single cycle model, you do have the link size somewhat turned to be significant. So that gets me to think, when in a single cycle model, when you don't have the future accounted for, maybe the overlapping issue is that this advantage of overlapping need to be captured in this parameter instead of canceled out in the end by in the main model. So it's really more like, on one hand, if you think that these are not very different model fit, and in a sense, it gives us understanding, okay, maybe these estimates are, they seem to be robust across all the models. So that could be saying, okay, in a sense, it gives you some more confidence on your result. Yeah, but
Got it. Yeah, I agree. Like maybe
I don't know what there's no listener number saying like if you are greater than 0.01 I just roll square, then you're much better. I mean, there's no such
like one metric
rule
just
of
to
thumb or anything.
that,
Yeah, it's just
it's more about like the explanation of each of the parameter, whether that makes sense or robust enough.
yeah, it's part of the assessment. Yeah,
Thank you.
sure.
Have you, I was interested in, well, the heterogeneity and the high performance drivers. Did you analyze the high performance drivers at all? Because I wonder. Your result of the fare and cost being different makes sense, right? Because the cost isn't as present or, visible. But I wonder if the high performance drivers are better at
That's, yeah, it's a good
recognizing
thought.
cost or not, I don't know. And then also, if you want to give advice to people, it would be good if you studied the high performance, because then you could try to help the other drivers by saying, these are the types of actions that are leading to high performance.
Yeah, that's definitely a good idea. We haven't done the yeah. This is only the base model. We start with it's yeah, the estimation actually still takes a lot of time, so overall, we're moving slowly, but
Then the other thing I wonder is just, I kept thinking about how the drivers behave, like I assume they have patterns, like do they have favorite places they try to go back to, because it's like fishing, right? Anyway.
Yeah, that's what I meant in terms of the latent classes, maybe,
Yeah.
when we look at their different patterns and we could give their behavior some categories, and people who always go to airport, who people who really want to just stay in the same place and circle around, and some people are more really like to, relocate. So having that kind of different classes and either as latent or not as latent. I mean, if you have their behavior, so you can label them directly, it'll be.
Yeah.
I think it'd be definitely
Yeah,
helpful.
that would be neat to try to segment them to some extent,
Yeah.
Would it be possible to use this model as the baseline model to do this pricing-based control? So like, this model reveals how driver reacts to the
Oh,
prices, right?
yeah, you definitely can.
So probably this is more realistic than many of these pricing-based control models that made a lot of assumptions about how drivers react to the price.
Yeah, I think that's the whole idea, that this can be a building block of a more prediction model that to be behaviorally more realistic. Yeah.
Great. Yeah. Okay. Any other questions from the audience? If not, let's conclude the seminar and thank you.
Thank you. I hope you get back tomorrow. Have you heard about your flight?
Yeah.
Oh, I haven't